Okay, hey, today we're gonna derive the Kalman filter for the general linear model, for the linear Gaussian model, so everything's nice and linear. So let the observation equation, observation equation is given by yt, zt, alpha t, where alpha t is the signal, plus epsilon t, where epsilon t is normally distributed with 0 and ht. Then the signal equation, or the signal dynamics, are given by alpha t plus 1 equals tt alpha t plus rt eta t, where eta t is normally distributed with 0 and qt. Now, what the Kalman filter does, it gives us recursions to calculate a t plus 1 and pt plus 1, where at plus 1 is the expected value of the signal at period t plus 1 given the information at time t, so given now. So we make a prediction for tomorrow given the information we have now. And pt is the variance of the signal tomorrow given today's information. So the Kalman filter gives us a recursion to calculate these estimates given initial guesses a1 and p1. So the actual Kalman filter is a series of 6 equations, or 5 equations, which is given by the first one is the prediction error. Vt is yt minus zt at, where at is our best guess of the signal at the time t given yt minus 1. The second equation is the variance of Vt given yt minus 1, which is supposedly given by zt pt zt prime plus ht. Then the third recursion is given by the Kalman gain, actually, which I'll write down later. And then we finally find at plus 1, so what we really want to calculate is given by tt at plus the Kalman gain times the prediction error. And for the last equation we find pt plus 1 equals tt pt, see, previous period, tt prime plus rt qt rt prime minus the Kalman gain times ft times ft times kt prime. The Kalman gain is tt pt zt prime ft minus 1. So this is basically this is kind of a setup, and this is the bulk, this is the actual Kalman filter, right? So here we have recursions, we have equations for at plus 1 in terms of at, and we have pt, we have equations for pt minus 1 in terms of pt. So this allows us to calculate like a2, p2, a3, p3, etc. until the end, if we know a1 and p1 in the beginning. So, well, let's start. Actually, these derivations seem very arcane, but they're actually very doable. So let's get started. So let's derive the first one. Okay, the first equation is given by Vt equals yt minus zt at. Right? So a prediction error, it makes sense that a prediction error of yt is defined as yt minus the expected value of yt given yt minus 1. So this is our prediction for yt. If we now simply substitute in the model, we find that you get zt alpha t plus epsilon t given yt minus 1, but this one is just 0. If we now take out the zt of the expected value, because zt is non-stochastic, we find exactly that this is by definition the definition of at, because at is defined as the expected value of alpha t given the information of the previous period. So this is our prediction for today's signal given yesterday. So we get Vt equals Yt minus Zt times At, which is exactly what we're after. That's the first one. So for the second one, we have to derive the variance of Vt given Yt minus 1. So if we just simply plug in our previous result, you find Yt minus Zt At given Yt minus 1. We find the variance of now plugging in the model Yt, Zt alpha t plus epsilon t minus Zt At given Yt minus 1, but actually At is defined as the expected value of alpha t given Yt minus 1, so actually Zt is non-stochastic, alpha t is known at this information set, so we can just completely disregard it. This means that we get the variance of Zt alpha t plus the variance of epsilon t plus some covariances, but they are 0. Hence we find Zt times the variance of alpha t given Yt minus 1 plus Zt prime plus Ht, where Ht is the variance of epsilon t. Hence we find that Zt Pt Zt prime plus Ht, because Pt is actually by definition the variance of alpha t given Yt minus 1, which we can see written exactly here. So that's the second equation. Done. Nice. Three more to go. We're going to derive the third and the fourth one together. So recall that the third one was the Kalman gain, which was Tt Pt Zt prime Ft minus 1. It seems very arcane. And the fourth one was the update for the At plus 1, which was given by Tt At plus Kt times Vt. So for At plus 1, we make a prediction based on the model and then adjust it based on the prediction error times the Kalman gain. That kind of intuitively makes sense. So to derive this, we use a result which says that the expected value of x given yz, where everything is normal, like x, y, and z are both normal, if y and z are orthogonal to each other, then we find the expected value of y given z is the expected value of x given y plus the covariance between x and z times the variance of z times z minus the mean of z. In our case, the mean of z is 0. Now, so we're just gonna continue by writing down the definition of At plus 1. So At plus 1 is by definition the expected value of alpha t plus 1 given Yt. Now to get it in this form, we split up the Yt information set. We're going to split it up in Yt minus 1 and Vt. So you get the expected value of alpha t plus 1 given Yt minus 1 and Vt. So we find that this is x, this is y, this is z. So to continue, we first need to find the sigma xz, which is the variance, is the covariance between Yt minus 1, alpha t plus 1 and the Vt given Yt minus 1. So this is just the covariance between t alpha t plus rt eta t, and this one was Yt minus Zt At, where we get the covariance between Tt alpha t plus Rt eta t times, if we now plug in the model for Yt, we find Zt alpha t plus epsilon t minus Zt At. So because everything is independent, normally distributed, this drops out, this drops out, this also drops out because At is known given Yt minus 1, we condition on Yt minus 1 here, and we find, using the standard covariance rules, Tt times the variance of alpha t given Yt minus 1 times Zt prime, which is equal to Tt Pt Zt prime. Now for sigma zz, this is simply the variance of Vt. But we already calculated that, and we found the expression Ft for this above. Remember? Here. This is basically Ft. This is Ft. Okay. So now, if we write down At again, so At plus 1 equals the expected value of alpha t plus 1 given Yt minus 1 and Vt, we use the lemma now, which says the expected value of alpha t plus 1 given Yt minus 1 plus the covariance matrix, which is Tt, Pt, Zt prime, times the inverse variance matrix, Ft inverse, times Vt. If we now plug in the model here, we find that you get alpha t plus 1 was given by Tt alpha t plus Rt eta t Yt minus 1 plus Tt, Pt, Zt prime, this is just standard algebra, Vt. But now the expectation of this is 0, and we find Tt times the expected value of alpha t given Yt minus 1 plus Tt, Pt, Zt prime, Ft inverse Vt. Ha! A lot of work, I realize. But this is by definition, this is again At, right? That's a very important definition. So we get Tt, At plus, and if we now take this, exactly this part, as the Kalman gain, Kt, we find the fourth equation, we find At plus 1 is Tt, At times Kt, Vt with exactly that Kalman gain. Then finally, for the last part, for the fifth equation, the fifth and final equation, we find that, recall that the fifth equation was given by Pt plus 1 equals the variance of alpha t plus 1 given Yt. We want to show that this equation is given by Tt, Pt, Tt prime plus Rt, Qt, Rt prime minus Kt, Ft, Kt prime. So there's a similar lemma for the variance of x given y and z, namely that this is equal to the variance of x given y minus, now minus, recall the minus is very important, the covariance matrix between x and z times the variance matrix of z, but now times again the covariance matrix primed. So it's very similar to the other lemma. Again, what we're now just gonna write down the variance of alpha t plus 1 given Yt, because this is simply the definition of Pt, and again we're gonna split up the Yt information set into Yt minus 1 and Vt, such that we find the variance of alpha t plus 1 is the variance of alpha t plus 1 given Yt minus 1, but now also minus covariance matrix between alpha t plus 1 and Vt times the variance matrix of V times the covariance matrix alpha t plus 1 and Vt primed. But we already calculated this. This one was Tt, Pt, Zt prime. This was Ft, or Ft inverse with an inverse. And if we now plug in the model here, we find the variance of T, alpha t plus Rt eta t given Yt minus 1 minus everything else. We get that we find, here we have, because these two are independent, we can just write Tt times the variance of alpha t given Yt minus 1, Tt prime, plus Rt Qt Rt prime, because this was distributed with as normally and normal 0 Qt, minus Tt Pt Zt prime, which is this part, Ft prime, Ft inverse, which is this part, and now we get this part primed. We get Zt Pt prime, Tt prime. So, but recall that this is the definition of PT, because PT is simply the variance of alpha t given yt minus 1 by definition. So we find TT, PT, TT prime plus RT, QT, RT prime minus, and now if we plug in, actually, if we plug an FT here and an FT prime as well, actually you see that this is exactly one of the Kalman gain, is exactly the Kalman gain described here, and here we have another Kalman gain but then primed, and we find exactly minus KT, FT, KT primed, which is exactly the fifth and the last equation. So just to recap, what we did, we derived the Kalman filter, which is a series of recursions to calculate AT plus 1 and PT plus 1, which are your best estimates of the signal in the next period given your information today. So we derived 5 equations which make up the standard linear Gaussian Kalman filter using only 2 lemmas actually, which make use of the properties of the normal distribution. So this is the first one, and the second lemma we used was to calculate the variance. Alright, thank you for watching. I hope you learned something. I had a lot of fun doing this. Thank you very much. Goodbye.